In a study conducted by Monique Santoso and Jeremy N. Bailenson from Stanford University's Department of Communication, the impact of mixed reality headsets with video pass-through functionality on users' perception was quantitatively analyzed. Building upon previous qualitative findings, the research aimed to explore the effects of video pass-through on self and others' perception. 40 participants were asked to complete a body transfer task twice. Once wearing the headset in video pass-through mode and once without it. The results indicate that using video pass-through can cause simulator sickness, create social absence, alter self-reported body schema, and distort distance perception. However, unlike past research, no perceptual aftereffects were observed. This study discusses the implications for the widespread adoption of mixed reality headsets and their impact on theories surrounding presence and body transfer. The findings have significant implications for the development and use of mixed reality technology, highlighting the need for further research into mitigating adverse effects while enhancing the benefits of immersive experiences. The proliferation of mixed reality headsets, such as the Meta Quest 3 and Apple Vision Pro, has enabled the seamless blending of virtual content with the physical world through video pass-through. This technology relies on high resolution, low latency, and real-time video displayed through headset screens, diverging from traditional see-through displays. Recent anecdotal evidence suggests that users experience simulator sickness symptoms, lapses in distance estimation, social absence, and body perception distortions when using pass-through. However, these findings lack quantitative support. This study aims to quantify these phenomena, situating them within psychology and communication theories, as well as the technological affordances of these headsets. We investigate the differences between pass-through and physical face-to-face interactions with oneself and others, a crucial yet underexplored area. By doing so, we provide a comprehensive understanding of the effects of video pass-through on user experiences, shedding light on the implications of this emerging technology. We focus on quantifying simulator sickness symptoms, such as nausea and eye strain, to provide a more precise understanding of the physical and psychological impacts of prolonged pass-through use. Our exploration of distance underestimation, social absence, and body perception distortions offers insights into the cognitive and social effects of this technology. By contextualizing these findings within psychology and communication theories, we elucidate the underlying mechanisms driving these phenomena. Ultimately, this study contributes to a deeper understanding of the consequences of video pass-through on human behavior, interaction, and perception, informing the development of more effective and user-friendly mixed reality headsets. Sensory conflict theory is often cited as a primary cause of simulator sickness, where conflicting information from visual, vestibular, and somatosensory systems disrupts normal intersensory interaction, leading to sickness. However, most simulator sickness studies focus on rendering 3D content and scenes, rather than real-time stereoscopic video of the real world. A recent study by Guo et al. Found only minor simulator sickness in pass-through video exergames, motivating our first research question: can short doses of video pass-through induce simulator sickness? Additionally, researchers have observed changes in individual body perceptions, including changes to body shape and size, in video pass-through compared to without the headset. These changes are attributed to distortions in the pass-through medium and the technological affordance of camera placement higher than the natural eye position. Previous work on body ownership and transfer in augmented reality has implemented the classic rubber hand experiment, demonstrating that individuals in AR do not report feeling as much ownership of their rubber hand as in the real-world setting. Other work using see-through HMD has found that participants experience body ownership with their mirrored virtual body in a virtual mirror. Our work aims to quantify the degree to which embodiment and body ownership are experienced in video pass-through when users view their physical bodies before a physical mirror, addressing our second research question. Furthermore, we examine how the perceptual system is impacted while wearing video pass-through and the aftereffects that occur once the headset is removed. Previous research has examined aftereffects in see-through video, showing that users would underreach for objects while wearing a see-through HMD and overcompensate by overreaching for objects once the headset was removed. In this study, we investigate the effects of video pass-through on the perceptual system, body ownership, and simulator sickness, building upon previous research in augmented reality and see-through video. In recent years, research has shed light on the impact of video pass-through on distance perception, revealing that distances are underestimated when using a headset compared to not wearing one. This underestimation is attributed to the limited field of view of the headset. Building upon these findings, this study seeks to quantitatively investigate the aftereffects of pass-through video on distance perception. It aims to explore how users perceive differences in distance in video pass-through versus the physical world, and how these effects change over time while wearing the headset and after its removal. Additionally, this study delves into the phenomenon of social absence, which refers to the decreased social connectedness and social presence experienced by users wearing augmented reality headsets in pass-through mode. This phenomenon was observed in previous work with the Microsoft HoloLens. The current study compares social absence in mixed reality versus without a headset in an experimenter-participant setting. The methodology employed in this study was approved by the Institutional Review Board at the institution blinded, with protocol number 66462. Participants used the Meta Quest 3 headset, which features 2064 by 2208 pixels per eye, a 110 by 96 degree field of view, 39 milliseconds latency, and a 120 Hz refresh rate, with full-color pass-through capabilities. Hand controllers were not utilized during the study. The procedure is designed to systematically examine the research questions, including RQ3, which focuses on the aftereffects of pass-through video, and RQ4, which explores social absence in mixed reality. The study utilized a repeated measures design, randomly assigning participants to either a pass-through followed by no headset condition or a no headset followed by pass-through condition. This was done to counterbalance order effects and assess the impact of each condition on body awareness and embodiment. Participants completed demographic questions and surveys about their past VR and pass-through experiences before the experiment. They then performed basic body awareness therapy and VR avatar body transfer exercises, designed to elicit feelings of body awareness and embodiment. These exercises involved rotating their torso, waving at their mirror image, walking in place, and standing still for 1,530 seconds in front of a mirror. Following these exercises, participants undertook a blind walk task to assess how accurately they could estimate distances. The total duration of wearing the headset for these exercises was 4 minutes. Figure 1 illustrates a participant wearing an MR head-mounted display and participating in body transfer exercises. This study employs a mixed design experiment to assess the impact of visual feedback on embodiment and presence in a virtual reality environment. Participants use an MR head-mounted display with a real-time video feed of their body. They perform a blind walk task towards a target point under 4 conditions. I, in headset. E, directly after removing headset. E, without a headset, and IV, without a headset for 3 more trials after the initial no headset condition. Following the first condition, participants fill out a post-experiment questionnaire on simulator sickness, presence, embodiment, change in perceived body schema, and body distortions. They then undergo the second condition and perform body transfer exercises before answering identical questions. The sample size calculation uses G-power with a power of 0.8, an effect size of 0.5, and an alpha error probability of 0.05. Resulting in a sample size requirement. This study aims to investigate how visual feedback influences the user's sense of embodiment and presence in VR environments, crucial for enhancing the overall VR experience and understanding potential applications in therapy, training, and entertainment. The recruitment process for participants involved a total of 40 individuals, with a mean age of 23.15 and a standard deviation of 4.45. Participants were recruited through the institution and online outreach, with remuneration offered in the form of a $25 gift card or course credit. Notably, 3 participants did not consent to video recording, resulting in their exclusion from the video analysis portion of the study. The demographic characteristics of the participants are detailed in Table 1, highlighting gender, race, ethnicity, and prior experience with virtual reality and pass-through technology. This section of the research paper outlines the measures employed to assess various aspects of participants' experiences in a pass-through augmented reality scenario. The blind walk task is used to measure distance perception, where participants are instructed to walk towards a previously seen target with their eyes closed under 4 conditions: pass-through, directly following pass-through, without a headset, and without a headset after initial trials. The difference between the perceived and actual target locations is recorded. Simulator sickness is evaluated using the Simulator Sickness Questionnaire, comprising 16 items across 3 subscales: nausea, oculomotor, and disorientation. The questionnaire utilizes a 4-point scale, and total scores are categorized into negligible, minimal, significant, concerning, and bad ranges. Sense of embodiment is assessed using an adapted avatar embodiment questionnaire, featuring 9 items on a 7-point scale. This questionnaire is modified to suit the pass-through scenario. Change in perceived body schema is measured using 6 items from the virtual embodiment questionnaire, employing a 7-point scale. This aspect examines the alteration in participants' perception and feeling towards the spatial representation of their body. Body distortion is evaluated with 4 items on a 5-point scale, examining the degree to which participants experience distortion in their body representation. Lastly, presence is measured using an adapted virtual human interaction lab presence scale, consisting of 3 subscales and a 5-point scale. This measure aims to capture the sense of immersion and presence participants experience in the pass-through environment. The study investigated the impact of VR headsets on the perception of one's body and its movements in a virtual environment. Researchers conducted a mixed methods experiment involving 40 participants, who performed various tasks with and without VR headsets. The dependent variables included embodiment, appearance, response, ownership, multisensory experience, and perceived change in body schema. The results were analyzed using the Wilcoxon-Sindrank test due to nonparametric data distribution, with outliers accounted for using the Winsorizing median statistical technique. The findings indicated that the VR headset significantly influenced the perception of response and perceived change in body schema, with higher scores in the no headset condition. However, there were no significant differences in embodiment, appearance, ownership, and multisensory experience between the 2 conditions. This suggests that VR headsets can alter the perception of one's body movements and overall experience in a virtual environment, particularly in terms of response and perceived change in body schema. The study's findings on the impact of video pass-through on simulator sickness are presented, addressing the first research question. Significant differences in simulator sickness were observed between participants using video pass-through and those without headsets. A Wilcoxon-Sindrank test compared each simulator sickness category, revealing higher nausea, oculomotor, and disorientation symptoms in the video pass-through group. Notably, the mean nausea score was 12.48 SD. 12.41 in the pass-through group, significantly higher than the 3.93 SD. 4.84 in the no headset group, p less than 0.05. Similarly, the mean oculomotor score was 20.60 SD. 17.39 in the pass-through group, significantly higher than the 6.89 SD. 7.73 in the no headset group, p less than 0.01. The mean disorientation score was 45.06 SD. 38.62 in the pass-through group, significantly higher than the 27.84 SD. 27.84 in the no headset group, p less than 0.001. The total simulator sickness score also showed a significant difference, with a mean score of 26.87 SD. 22.22 in the pass-through group compared to 9.44 SD. 9.21 in the no headset group, p less than 0.01. These results suggest that even short-term use of video pass-through can induce simulator sickness, supporting the author's hypothesis. The findings are summarized in a table, providing a clear overview of the mean scores and standard deviations for each simulator sickness category in both groups. The researchers investigate the effects of pass-through, a feature in augmented reality (AR) headsets, on simulator sickness and users' sense of embodiment. They report that even short exposure to pass-through can induce simulator sickness, as shown in Figure 3, which presents a bar plot of simulator sickness scores categorized by severity. The results reveal that participants experienced changes in their perceived body schema and body distortions when using video pass-through, as compared to not wearing a headset. To quantify these effects, the researchers conducted a Wilcoxon-Signed test, which found no significant differences in participants' sense of embodiment between the two conditions. However, a significant increase in perceived body schema changes was observed in video pass-through, m equals 3.06. SD equals 1.53, compared to without a headset. M equals 2.21, SD equals 1.28. Furthermore, participants reported higher body distortions in video pass-through, M equals 2.01, SD equals 0.95, versus without a headset, M equals 1.13, SD equals 0.28. These findings have implications for the design of AR systems, highlighting the need to consider the potential effects of pass-through on user experience and comfort. The study examines the effect of video pass-through on distance estimation in augmented reality. It investigates whether distance underestimation persists after removing the headset following a video pass-through experience. A linear mixed effects model was used to analyze the data, considering trial time as a continuous variable and condition order. The results showed no changes in the pattern of results by trial time and order. Participants significantly underestimated distances while using the pass-through compared to estimating distances without a headset. The underestimation persisted, with participants underestimating distances less by 21.27 centimeters after removing the headset compared to during pass-through. Significant differences were also found when comparing distance underestimation in pass-through and no headset conditions, with an underestimation reduction of 8.85 centimeters. These findings suggest that video pass-through in augmented reality can lead to significant underestimation of distances, which persists to some extent even after removing the headset. This has implications for the design and calibration of augmented reality systems aimed at enhancing spatial awareness and navigation. In the study, researchers explored the correlation between social presence scores and distance underestimation in video pass-through versus without a headset, addressing the fourth research question. They employed a Wilcoxon-Signed test, a non-parametric statistical test suitable for paired data, to achieve this. The results revealed a statistically significant difference in social presence scores, with a median increase of 30.55% when participants did not wear a headset. M equals 2.48, SD equals 0.99, compared to when they used video pass-through, M equals 3.08, SD equals 1.22, with a test statistic of W equals 17.50 and P less than 0.001. Figure 5 illustrates the difference in distance underestimation, providing a visual representation of the findings. The results suggest that wearing a headset in video pass-through leads to a decrease in social presence, implying that individuals feel more socially absent when using this technology. The findings have significant implications for the design of virtual reality systems, highlighting the importance of considering the impact of headset usage on social presence in virtual environments. This study's discussion section delves into the psychological and behavioral effects of video pass-through, drawing from psychology and communication theories, as well as device affordances. A key objective is to compare face-to-face interaction with video pass-through as a medium, an area that has received limited attention in prior literature. The body transfer exercises employed in the study procedure aim to induce a sense of embodiment and body awareness in participants. The results indicate that there were no significant differences in participants' embodiment in their physical bodies between the pass-through and without headset conditions. However, a notable finding emerges when examining users' perceived body schema and body distortion. Specifically, the study reveals a change in users' perceived body schema and body distortion while in pass-through compared to physical reality. This phenomenon may be attributed to the curvature of the small screens in the headset, which can influence users' perception of their body. The mean social presence scores in the two conditions, without headset and in pass-through, are illustrated in Figure 5, showcasing the difference between the two conditions. This study's findings contribute to the understanding of the psychological and behavioral effects of video pass-through, highlighting the importance of considering device affordances and their impact on user psychology. The results have implications for the design of mixed reality experiences, emphasizing the need to account for the potential effects of video pass-through on users' perception of their body and surroundings. The research paper under discussion delves into the integration of multiple camera streams in mixed reality (MR) headsets, revealing discrepancies between user eye location and camera display location. This distortion significantly impacts body perceptions, particularly in mixed reality interventions on body image. The study reveals that even brief durations of MR headset use can trigger simulator sickness, with disorientation being the primary contributor. This supports the sensory conflict theory, which attributes the issue to technical features such as lower refresh rates and resolution compared to the human eye. Furthermore, the findings underscore the need for caution in the use of video pass-through in motion due to distance underestimation. Interestingly, the study shows no significant aftereffects from a short headset experience. The research extends prior literature on simulator sickness and its relation to MR headsets, suggesting further comparisons between video pass-through and non-zero headset baselines, as well as the influence of seeing oneself in a mirror on sickness levels. The study investigates the social implications of video pass-through in mixed reality (MR) headsets, focusing on the phenomenon of social absence. Users in pass-through mode may treat face-to-face interactions similarly to virtual reality (VR) experiences, feeling psychologically removed from the real world. This could be attributed to the limited field of view and lower visual fidelity of physical surroundings in pass-through mode. The concept of social presence in MR is crucial for understanding social facilitation and inhibition processes in pass-through interactions. The study explores social absence in experimenter pass-through user interactions, leaving room for future research on dyadic and group interactions. The results suggest that despite technological advancements, perceptual and social effects will limit video pass-through adoption as an everyday medium for augmenting physical world interactions. Longitudinal studies are necessary to understand how to minimize simulator sickness and psychological factors like social absence. The study emphasizes the need for further research into video pass-through immersion, highlighting the importance of understanding the interplay between physiological and psychological factors in MR interactions. The page delves into the diverse methodologies and algorithms employed in the field of computational neuroscience, focusing on the analysis of neural networks. It emphasizes the importance of understanding these complex systems, which are fundamental to comprehending cognitive processes and developing artificial intelligence. The discussion centers around two primary approaches: the bottom-up and top-down methods. The bottom-up approach involves the construction of models from basic components, such as neurons and synapses, to simulate the behavior of larger neural networks. This strategy is beneficial for understanding the fundamental principles governing neural systems but can be computationally intensive. On the other hand, the top-down approach involves the analysis of large-scale neural networks to deduce the underlying principles. This method is more suitable for understanding complex cognitive processes but may lack the precision offered by the bottom-up approach. The page also highlights the role of mathematical modeling in computational neuroscience. It explains how mathematical equations can be used to describe the behavior of neurons and their interactions within a network. These models are crucial for making predictions about neural system behavior and for guiding experimental research. Furthermore, the text touches upon the significance of machine learning in computational neuroscience. Machine learning algorithms can be used to analyze large datasets of neural activity, enabling researchers to identify patterns and make predictions about future behaviors. In conclusion, the page provides an in-depth exploration of the methodologies and algorithms used in computational neuroscience, emphasizing their importance in advancing our understanding of neural systems and cognitive processes. This section of the research paper discusses various studies related to the impact of augmented reality (AR) on human perception and interaction. It begins by referencing Guo et al.'s study on the effect of pass-through in shared spaces on player performance and experience in VR XR games, published in the IEEE Transactions on Visualization and Computer Graphics in 2024. The discussion continues with Scola and Learokopoulos' examination of body ownership in immersive virtual and augmented reality environments, as presented in the Visual Computer in 2016. Virtual reality, embodiment, and body awareness are interconnected concepts that have garnered significant attention in recent research. This focus stems from the potential of virtual reality to alter users' perceptions of their bodies and surroundings, leading to novel applications in fields such as therapy, education, and entertainment. One key framework in this realm is the body transfer illusion, which occurs when users perceive a virtual body as their own. This phenomenon is achieved through synchronous visio-tactile stimulation, where the virtual body is subjected to the same sensory inputs as the user's physical body. Studies have demonstrated that the body transfer illusion can induce changes in body ownership, self-identification, and even empathy. Another crucial concept is embodiment, which refers to the sense of owning and controlling one's body. In virtual reality, embodiment is fostered through the use of controllers that track users' movements, allowing them to interact with virtual environments in a natural and intuitive manner. Research has shown that enhanced embodiment in virtual reality can lead to improved motor skills, reduced anxiety, and increased feelings of presence. A related area of investigation is body awareness, which encompasses the ability to perceive and understand one's bodily state. In virtual reality, body awareness is critical for maintaining a sense of immersion and preventing motion sickness. Studies have explored the use of haptic feedback, visual cues, and other sensory inputs to enhance body awareness in virtual environments. The understanding of these concepts is crucial for the development of effective virtual reality systems that can induce a sense of presence, improve user experience, and unlock the full potential of virtual reality technology. Further research is needed to fully elucidate the complex relationships between virtual reality, embodiment, and body awareness, and to explore the vast array of applications that these concepts enable. Recent advancements in virtual reality and augmented reality have led to significant findings, particularly in the realm of personalized virtual humans. A study highlights the importance of plausibility and perception for user experience, demonstrating that photorealistic avatars can influence body weight perception in females. Embodiment and selective visual attention play crucial roles in self-perception, with individuals experiencing higher body dissatisfaction perceiving their avatars as more realistic. User experience in virtual reality is also a key area of research, with frame rate significantly impacting user experience, performance, and simulator sickness. The development of virtual reality driving simulators using head-mounted displays offers potential benefits, including enhanced driving skills and reduced simulator sickness. Measuring presence and simulator sickness in first-person virtual reality games is another area of focus, with walking in virtual reality games presenting unique challenges. The application of virtual reality in clinical research is another promising area, with assessments of pre-exposure cyber sickness within chronic pain populations offering valuable insights. However, challenges persist, and further research is needed to fully realize the potential of virtual and augmented reality. Overall, this research provides a comprehensive overview of the complexities of user experience, perception, and potential applications in various domains, shedding light on the latest trends and findings in the field. In augmented reality, the interplay between display, shadow, and position significantly influences depth perception. Building upon foundational research, such as Adams et al.'s examination of depth perception in AR and Renner et al.'s comprehensive review of egocentric distances, this study delves into the complex relationships between these factors. The display factor encompasses various aspects, including resolution, field of view, and latency, all of which impact the user's ability to accurately perceive depth. Shadows, both cast and attached, play a crucial role in providing cues for depth perception, with attached shadows being particularly effective in enhancing the sense of depth. Position, encompassing both egocentric and allocentric distances, further complicates the depth perception landscape. Egocentric distances, referring to the distance between the user and an object, are influenced by the user's body position and movement. Allocentric distances, on the other hand, involve the relationships between objects in the environment. The study draws insights from Whitmer and Klein's work on judging perceived and traversed distance in virtual environments, highlighting the importance of considering both types of distances in AR applications. By examining the interactions between display, shadow, and position, this research provides a nuanced understanding of depth perception in AR, ultimately informing the development of more immersive and realistic AR experiences. The findings of this study have significant implications for AR application design, underscoring the need for careful consideration of display, shadow, and position factors to create an optimal user experience. Furthermore, the research highlights the importance of continued investigation into the complexities of depth perception in AR, with potential avenues for future work including the exploration of individual differences in depth perception and the development of more sophisticated algorithms for depth Q integration. To assess participants' sense of embodiment, researchers employed the body transfer task and the adapted embodiment questionnaire. The body transfer task consisted of a series of exercises adapted from previous studies, designed to elicit body awareness and a sense of embodiment. Participants performed exercises such as waving their arms, walking in place, and stretching to stimulate body awareness. The adapted embodiment questionnaire, modified from Gonzalez-Franco and Peck, comprised 9 items that measured participants' feelings of embodiment. These items probed sensations such as feeling out of one's body, feeling as if movements were influencing each other, and feeling as if one's body was changing to resemble the mirror digital self-representation. Additionally, the body distortion scale, with a reliable alpha value of 0.79, assessed the sensation of limbs being attached in the wrong locations. By leveraging these tools, researchers explored participants' experiences in the pass-through scenario, providing valuable insights into their sense of embodiment. This study delves into the concept of presence in virtual reality, with a specific focus on how pass-through technology influences self-perception and body awareness. Employing a mixed methods approach, researchers combined qualitative and quantitative data to explore this phenomenon. Qualitative feedback from participants revealed 4 primary themes: abnormal bodily sensations, mismatch between the pass-through image and real-world self-perception, distortion of body image, and altered self-perception. These findings suggest that pass-through technology can significantly impact an individual's sense of body awareness and self-perception. To quantify presence, the study utilized the Adapted Virtual Human Interaction Lab (VHIL) presence scale. This scale assesses social, self, and spatial presence on a 5-point Likert scale, comprising statements such as, "It felt like the experimenter was in the room with me," and "I felt that my digital mirror self-representation represented me." This scale enables researchers to objectively measure the degree of presence experienced by participants in virtual environments. The use of pass-through technology and its subsequent distortion of body image raise important questions about the implications of virtual reality on self-perception and body awareness. The findings of this study contribute to our understanding of the complex interplay between technology, self-perception, and presence in virtual environments. The study's results have significant implications for the development of virtual reality applications, particularly those that incorporate pass-through technology. The researchers' use of a mixed methods approach provides a comprehensive understanding of the phenomenon, highlighting the need for further research into the psychological and philosophical implications of virtual reality on human perception and experience.